All right, well, today I want to talk about quaternions. So with various objects that we have here, we have on the transform, it says rotation, and we have the X, Y, and Z, and these are the Euler angles, the rotation about the X-axis, rotation about the Y-axis, and rotation about the Z-axis. And this is a very intuitive form of representation, but it does have some problems. In particular, it suffers from something called gimbal lock, a feature of gyroscopes that when they're turned to a certain angle, they would all of a sudden leap from one orientation to another, and there'd be a big bang in the device, and it was not good mechanically. It's called gimbal lock. The problem is that the values of the Euler angles switch abruptly. And I'll show you this in this little example here. With the X, Y, and Z keys, I can change the rotation about X, rotation about Y, rotation about Z. And these angles increase constantly. So once they get to 360, they go to 361 and so forth. But then I'm looking up the value of the Euler angles and displaying it in these three sliders here. And so if I play this, and now I press the X key, which rotates it about the X-axis, you see that at that point, it abruptly switched the Y and Z's to 180. If I do the S key, it goes back down again. And so you can see, even though the orientation of the object is not changing abruptly, its representation in terms of Euler angles is changing abruptly. So a better representation of an orientation, and the one that is used internally by Unity, is called the Quaternion. This is what that little program is doing. There are two different versions of it. One where I'm assigning the Euler angles with vector 3, and the other where I'm assigning the rotation of the object with this Quaternion Euler angles wrote X, Y, and Z. They're functionally identical. And then I look up the rotation and the angles, which is what is displayed over here. Quaternions are based on complex numbers, and they have 4 components, and we refer to these as X, Y, Z, and W. And only very rarely would we access these components directly, because you've got to know a lot about what's going on in order to do it. Mainly what we do is take existing rotations. So for instance, transform.rotation is a quaternion. So I could get the orientation of my object by looking up its transform rotation. And then from that quaternion, I can construct new rotations, new orientations, and in particular, we use this to interpolate smoothly between 2 different orientations. If we were to try and interpolate smoothly between these with Euler angles, these abrupt changes make it difficult to interpolate, since it's changing abruptly from 0 to 180. The other thing to notice here is here I'm increasing the X angle. When it gets to 90, it switches and it starts going back down again. So it's not, even though I'm continuing to increase the X angle, its representation in Euler angle is going back down. All kinds of strange issues with the Euler angles. So what a quaternion is it's kind of a 3-dimensional analog to the ordinary complex number, A plus BI, where A is real, B is imaginary, and this I number has the magical property that it times itself is equal to -1. That's the imaginary number I. And when we do complex multiplication of a real time, or a complex times a complex, we get a squared plus 2abi plus b squared times I. So the real parts, the a and b, get kind of scrambled together into the real part of the product, and the real and imaginary parts get scrambled together into the imaginary part of the result. Now, quaternions are like complex numbers, except that they have now 3 complex numbers, I, j, and k. And when we do the multiplication of this 4-entity item, like the complex multiplication of these 2-entity items, we get all kinds of mixing of the different terms. And I, j, and k are imaginary numbers in the sense that I times itself, j times itself, and k times itself are all equal to -1. And that the mixed products of I and j is equal to k, j times k is equal to I, and k times I is equal to -j. So there's a whole bunch of arithmetic that goes with doing quaternion products. But the bottom line is that a quaternion multiplication results in a dot product, which is a scalar, and a cross product, which is a vector. And so the idea is that a quaternion is a scalar w and a vector x, y, and z. And you might be familiar with the use of the ijk unit vectors in Cartesian space, and that's where they come from. They come from quaternions. In addition, the definition of the cross product comes out of this quaternion multiplication. So that's where all of the machinery that we're familiar with comes from. Now, a quaternion represents a rotation by an angle A about a unit vector u, where the unit vector u is represented by the x, y, and z, and the angle A is represented by the w. And the w is the cosine of the angle over 2, and the x, y, and z are the unit vector u times the sine of the angle a over 2. All very complicated. Thankfully, we don't really need to know much about how this works because Unity does all this behind the scenes, and we can continue to think in terms of Euler angles, but we'll use quaternions all the time. One thing about quaternions as their rotation representation is that if you multiply 2 rotations, you get a rotation. So if I rotate something like this and then rotate something like this, it's the product of those 2 is going to be the same as the direct rotation between them. We also find with quaternions that if we multiply a quaternion times a vector, we get the rotated vector. So a quaternion times a vector will rotate that vector. The various properties of the quaternion class, first of all, we have the x, y, z, and w components of the rotation. And these are shown down here as I do this rotation, the x, y, z, and w component of my rotations. There are various methods in the quaternion class, one of which is Euler angles, that returns a vector 3 of the Euler angles of a rotation. There's the quaternion identity, which is a rotation that corresponds to no rotation. That is the x, y, and z axes of the object, the right, up, and forward directions of an object are aligned with the X, Y, and Z of the world, in which case the Euler angles are all 0, and our quaternion identity is 0, 0, 0, 1. 1 is the W, that's the cosine of angle 0 over 2. Cosine of 0 is 1, plus the sine of 0, which is 0 times any vector, is 0, 0, 0. So those methods. Before I go on to the other methods, let me again show you what's happening here. So as I rotate this little thing and the Euler angles jump around, the thing to notice is down here that these things are moving continuously, changing continuously. And I'll press the Z and the Y as well, which is now tumbling it around its different axes. And you see the Euler angles jumping all over the place here as things move around. But the Quaternion itself, everything is moving smoothly and continuously among different orientations. So the Quaternion representation is good for interpolating rotations from one to another. So functions that we get with the Quaternion class, there's look rotation, angle, Euler, slurp, and from to rotation. Look rotation acts kind of like the transform look at. We have a vector forward and a vector upwards, and this creates a rotation that looks along this direction with the head up in this direction. And this one, the second one, is optional. It's by default vector up, but you can make it anything you want. Here's an example of a look rotation. The Quaternion angle returns the angle in degrees between two rotations. So you have two orientations like this, and it returns the angle between these two. Quaternion Euler is a way of setting a quaternion by specifying the Euler angles. There are two versions. There's the 3-argument scalars and the 1-argument vector 3. And this returns a rotation that rotates in a particular order, first about the Z, then about the X, and then about the Y. That's a convention because different orders would lead to different orientations. So here's a rotation about the Y-axis by 30 degrees. Slurp is an interesting one. Slurp stands for spherical linear interpolation. And this interpolates between two quaternions. So we have quaternions representing two different orientations, from and to. And as we change this third parameter, t, from 0 to 1, it interpolates from the first one to the second one. With t equals 0, it's all from. With t equal 1, it's all to, and we interpolate in between these. So here's an example of slurp. We have a from rotation and a to rotation specified as two transforms that we're getting the rotation from. And the third parameter, t, is time.time times the speed. So when we start this, time, of course, starts at 0. I'm scaling the increasing time by this speed variable. And so it progresses from the from rotation to the to rotation as time passes in the game. And I believe there's an example of this somewhere here. Number 3. So here I have little objects that are rotating to, from and to. Another way to do this is one way to do this where we have a from and a to rotation and a time that is increasing. This, of course, the problem is the time. If you were to start this at some time other than 0, this would already be at the 2 rotation. So another way to do this is to take the object's rotation as the from and move it towards the 2 by time dot delta time times speed. This is the small quantity, the time between frames, and this is the speed, the scaling factor as to how rapidly we move toward it. In this case, the transform rotation is replaced progressively, each time moving a little closer to the 2 rotation that we're seeking. And I think I actually, no, here's this one. So here, the red one is moving progressively towards the orientation of the blue. And so you notice that the green one kind of goes there directly, whereas this one gets closer and closer, never actually reaching it. Well, it does eventually, but it does this because it's continuously replacing the rotation as it moves toward the 2 rotation by this small quantity. There's also a vector slurp. Quaternion slurp interpolates between 2 orientations. Vector slurp interpolates between 2 vectors. And it works exactly the same way. There's a from, a to, and a t parameter that goes from 0 to 1. I applied this in our switch to the closest. So I had this little game here where when I press this, it switched to the closest one. And what I've done here is I have my light pointing. I have 2 lights actually. I have a yellow and a green light. And of course, when the 2 of them combine, it makes a yellow little footprint. And you can see the spherical interpolation between these vectors. That's the green. And there's also a lerp, linear interpolation. So here's slurp, the spherical interpolation. It interpolates on a great sphere. And there's linear interpolation that linearly interpolates the various components of our vector. And so as I move this thing around, it moves spherically or linearly from one to the other. And so you can see the difference between the 2 different interpolation schemes. There's a linear Quaternion interpolation too. Another is the from to rotation. This takes 2 directions, 2 vector directions, and it figures out what rotation would move you from the from direction to the to direction. So it creates a rotation that you can then use to move things around. This one sets the rotation so that the vector up points along the transforms forward. And I believe there's an example for this too. This one. So I have these 2 blue objects. One of them is using linear interpolation. The other one is using spherical interpolation. I have options of doing it progressively, which is where the rotation gets updated each step, or doing it based on the value of time dot time. And I have these 2 others that are just following the blue ones. What we'll see up here in the text is the difference between the Quaternions as they go linearly and spherically from one orientation to the next. The differences are fairly subtle, but they do differ by a few degrees. The numbers here are difference. Here's the angle difference between them, which is a maximum of about 10 degrees angular difference between the two of them. And there they're settling down. And the other two here that are following them along slowly eventually reach it too. So Quaternions, it's important to understand what they are. It's not like we're going to manipulate them directly, but these are the tools that we use to move smoothly from one orientation to another, as opposed to the Euler angles that suffer from gimbal lock. So I'm going to stop sharing at this point, and I'm going to end the recording, and I'll see you all in class. Bye.